So in the previous video, we defined the second first-order derivative for function f. In this video, we're going to argue that the second derivative, which I recall, is a bilinear operator from the vector space V, where the domain of f is, the vector space W. We're going to show that this bilinear transformation is actually symmetric when it's continuous. Okay, I have to clarify that, but basically symmetry means that, okay, the bilinear transformation has two arguments, and symmetry means that the order of these arguments doesn't change the result. So, okay, let's have a precise statement. So we have a function, as usual, it's a function, between Banach spaces, so V is a Banach space, W is a Banach space, U is an open set in V, and F is a function from the open set U to W. And it's 2 times differentiable. What does that mean? Well, remember, that means that for any point in U, right, for any x in here, there is a bilinear transformation that's bounded from V to W. So D to F associates with each point x a bilinear transformation. And the claim of the theorem is that if the second derivative is continuous at x naught, right? If d2f of x depends continually on x around x naught, then we have the symmetry property that I wrote in the previous slide. So there's an important application of that to the setting of calculus, which we discussed at the end of the previous video. Remember that in that case we have the Hessian matrix, and the Hessian matrix defines a bilinear form. So the symmetry of the second derivative means that the Hessian matrix is symmetric. And that's whenever the partial derivatives of second order are continuous. So in order for the first-order derivative to be second order to be continuous at x naught, you need the partial derivatives to be continuous at x naught. And if that's the case, then the Hessian matrix has to be symmetric. Which really means that, taking a partial derivative with respect to y or with respect to j, the order is not going to matter. Okay, so let's know what's going on, okay? Let's see what's going on. Okay, first of all, we're assuming that f is differentiable at any point x in u, right? So if you want a second derivative, we better have a first derivative. The first derivative for each x is a linear transformation from V to W. Therefore, I can associate with any point in U, x, a linear transformation, and that's the map df, mapping x to dfx. That's well defined. We're also assuming that f is twice differentiable, and that really means that there's a second derivative. Remember that we have the derivative of f at x, and that by some isomorphism, some isometry, is a bilinear form. So for each point x in my domain, I have a bounded bilinear operator from V to W. That's d2f of x, and that's well defined for all x. Right? That's so far I've just said that f is 2 times differentiable. Now there's something more, which is the assumption of continuity. What does continuity mean? And that might actually sound a bit confusing because, okay, you can think, okay, I wouldn't be saying that the derivative is a bilinear operator that's bounded, and aren't all bilinear operators continuous? All bounded bilinear operators continuous, sorry. Well, it's not about that, right? So the continuity statement in the title is a continuity in x. So it's not about what happens if I compute d2f of x at vectors v1 and v2, and how the bilinear transformation depends on v1 and v2. That continuity is granted. But we're assuming something more. We're assuming that if we look at, okay, second derivative of x minus second derivative of at x naught, when x converges to x naught, this goes to 0 in norm, in the norm of this Banach space of bounded bilinear transformations. So let me just remark, because we know that differentiable functions must be continuous, well, if there is a second derivative, there is a derivative to df, therefore df is continuous. So that's all there is to this statement here. And of course, this is not v2, this is v, sorry. So, okay. Hopefully it's clear. Okay, at any fixed x, d2f of x is a continuous function of v1 and v2. Well, we want this continuous function to depend continuously on x at the point x0. Okay, so watch. So we're going to prove this by a proof that it's slightly awkward to write, because if I wanted to explain this, I would have to start from Taylor series, which is a subject that we haven't seen yet. So I'm just going to present it to you like a little bit of a mystery. I'm going to define this function phi that maps a pair of points t1 and t2, both in the interval from minus delta to delta. So these are real numbers, right? And it maps to this funny thing here. F of x0 plus t1 v1 plus t2 v2, and then you subtract f of x0 plus t1 v1 minus f of x0 t2 v2 plus f of x0. And the claim is that if I compute this function at t and s and divide by ts and send t and s to 0, I get the second derivative computed at v1 and v2. v1 and v2 are these vectors over here, right? Which I fixed from the get-go. Okay, so first of all, why do I take this function? Why should this be true, right? So it's basically that when we look at all these things, we're gonna, okay, let me just say, okay, if you know what a Taylor series is, we're gonna come back to that later in the class. If we know what a Taylor series should be in this case of functions over Banach spaces, then this formula should make sense. This limit here should make sense. Otherwise, let's just accept it, and we'll see how everything shows up. Okay. So, but okay, why do I want to prove this claim? Remember, I want to prove that the second derivative is symmetric, meaning that if I swap v1 and v2, I get the same value. Well, if I have the claim, then I have the symmetry, right? So, and let me actually call these guys here t1 and t2. Sorry, t1 and t2. And this is going to be t1, t2 going to 0. So if I switch t1 and t2, that's like swapping v1 and v2. So the limit of phi of t2, t1 divided by t1, t2, or t2, t1 is going to be the second derivative computed at v2, v1, right? So there's a swap here. Now, that's for any sequence of values t1 going to 0, any sequence t2 going to 0. Therefore, if I look at phi of t and t divided by t squared, I have that, well, by the claim, it's equal to this. And by the swapping argument, it's also equal to this. And because the limit is uniquely defined, then I have the equality here that I want to prove. Perhaps let me mention something that's in the previous slide, that in order to speak of this function phi, I need everything to be well defined, but that just comes from the fact that x0 is an open set, and therefore if I walk a little bit in the direction of v1, or walk a little bit in x0 plus t2 v2, or if I walk a little bit in the direction, x0 plus c1 v1 plus c2 v2, I can assure that all of these things lie inside the set U if delta is small enough. So that's what's over here. So I'm not going to worry explicitly about that, but it's important to know that this phi is well defined. Therefore, I'm not trying to compute f at a point that's outside the domain U. Okay, so we're going to prove the claim now. So we have to prove this limit. And we're going to use the mean value inequality, right? So which actually, let me write it in this more general form. Mean value inequality says that if I have a function defined over a subset of the real line, an interval, from that interval to w, then I can bound the difference between gamma of b and gamma of a by the distance between b and a and the superderivative over points in between a and b. Now this interval could be ab or ba depending on which one is smaller, but we're not going to worry about that too much. Okay, how are we going to use the mean value inequality? So I want to look at this expression here. This is an expression that depends on both t1 and t2. So in order to apply the mean value inequality, I'm going to hold t1 fixed. And I'm going to let t2 vary. That's what's over here. Now, this would be my function gamma of t2, which I'm going to differentiate. And notice that gamma of 0 is 0, because when I take t2 equals to 0, well, we have to come back here and check the formula. Right? T2 equals to 0 means that this term and this term are equal. And so this term and this term, except for the signs, right? So everything exactly cancels. So I'm going to apply it to this function, gamma of t2, and gamma of 0 is 0. So to apply the mean value inequality, you need to compute the derivative. And I'm just going to say that, I'm going to compute the derivative, but I'm going to write it as a partial derivative. So I have phi of t1 delta 2. That just means that I'm taking derivative in theta 2, keeping t1 fixed, right? And phi is this complicated formula. So I get a derivative of this term. This doesn't have t2, so it's not going to count. I'm going to get this term and this other term that doesn't contain t2 either. So these two terms are going to disappear. I'm going to be left with the other two. And how do I compute the derivative? Well, I'm going to use the fact that I know that there's a relationship between directional derivatives and the Fréchet derivative. So we know that if f is Fréchet differentiable, then it's also Gâteau differentiable, and the Gâteau derivative corresponds to the Fréchet derivative. So if you apply that and you think a little bit, so the derivative of this guy is just the Fréchet derivative of f applied to v2, right? Compute the Fréchet derivative at this point, similar for this guy, and then I get this, which is also this. So 2, 2, 1, 1. So just have to think of, if you like, you write the limits and you'd see that you get whatever you should get. Okay, so, okay, good. So now I have the derivative, and how I'm going to use that? I'm going to just say that this function, remember that I've called this gamma of t2, because I'm keeping t1 fixed. And here's gamma of 0, because when t2 is equal to 0, then everything's 0. So, okay, this whole expression is less than the distance, right? I'm moving from 0 to t2. So that's like b minus a is equal to absolute value of t2, right? So the absolute value of b minus a. And then I have to take the sup of the derivative in terms of theta 2 in between. And I'm just going to say, well, theta 2 is a number between 0 and t2, so it has absolute value less than the absolute value of t2. So that's what I wrote over here. And I have the formula for the derivative, right? So I have the derivative over here. And of course, I can put these terms together just because I know I can add and subtract linear transformations. Of course, the Fréchet derivative is a linear transformation. So I have two linear transformations here applied to the same vector v2. And this is what I get. So it's a sup over theta 2 less than t2. And now I have to look at this term. And I'm going to apply again the same trick. Notice that I have here a second derivative. Here now I used to have f, now I have a first derivative. I'm going to use the second derivative, or the derivative of df, to bound this. So now I look, I have a sup over theta 2 here, and I want to estimate this quantity. So I'm going to fix some theta 2, with theta 2 less than the absolute value of t2. And I'm going to differentiate the function that I had in the previous slide, which is eta theta 1 theta 2, this whole thing. Remember, I'm interested in this function when I have theta 2 and t1. That's basically what shows up here. But for now, I don't need that. I just have this function. I'm going to differentiate it. Again, I have something that when I set theta 1 equals to 0, this is exactly 0, right? So this is equal to this, and this is going to be 0, so everything disappears. So let's compute the partial derivative with respect to theta 1. It's really a derivative with respect to theta 1 when theta 2 is fixed. So now here I need a little bit of an exercise, which is that I can move this derivative, which is just, a limit of quotients and everything. I can move this derivative inside, really. Here I'm differentiating the product between a linear transformation and a fixed vector. Here I differentiate first the linear transformation, and then I apply it to a vector. And I claim these two things are the same thing. And that, again, you can just write the limits down and check that everything works. I mean, you have to make sure that you understand that these guys, if you look at the quotients, they converge according to the norm over the space of linear transformations, so everything works out. So you have some sort of continuity here that allows you to pass the limit inside. Okay, but accepting that, we have to differentiate this this thing, right? So this is just, this guy here is just this term, which I'm differentiating with respect to theta 2. And I'm going to apply the chain rule again, right? So if I differentiate, I'm differentiating with respect to theta 1 here. I fix theta 2 and I'm differentiating with respect to theta 1. And now if I apply, right, what do I get? When I differentiate df, I get the derivative of df, and I have to differentiate what's inside, right? So I have theta 1 v1, so I get a v1 outside. And I get d of df applied to v1, which I then apply to v2, minus the other term, which is just trivial, right? It's just this guy multiplied by this guy multiplied by theta 1. So when I differentiate, theta 1 disappears. It's just like regular calculus. I mean, you can check it if you like, but it doesn't amount to much. Now there comes a critical juncture. Remember, what does this expression mean? Well, this guy here, the derivative of the derivative, is a linear transformation from V to the set of bounded linear transformation from V to W. And we know there's this isomorphism that allows us to switch from ddf to d2f, which converts a bounded linear transformation from V to LVW into a bounded bilinear transformation, which is d2f. So I get that this whole thing here becomes this whole thing here. So I have d2f computed at x naught plus theta 1 plus theta 2, theta 1 v1, theta 2 v2, applied v1 to v2, minus the second derivative of x naught applied to the same pair of vectors. And now, again, remember that this eta is 0 when theta 1 equals 0. The zeta of theta 1, so this is zeta of 0, theta 2. I'm looking at the difference, which I want to bound in norm. I'm just going to use the mean value inequality again. Now that I know how to differentiate things, I get T1, and I get the soup. This is just partial derivative of eta with respect to theta 1. And I've just put the two bilinear forms together. Bilinear forms add and subtract, so I get this. But remember, we're interested in the soup of this expression when theta 2 is less than T2 in absolute value. Remember that we're interested in this bound for this guy, and the bound we got is this expression here. So this thing that showed up here, I can finally, this would be eta of T1 theta 2. And luckily, that's precisely what we just bounded over here. Eta of T1 theta 2 is less than or equal to this. So I can put everything together. And if you do it carefully, you get exactly what I have here. You get phi of T1 T2 minus T1 T2, second derivative f at x naught applied to v1 v2. Well, that's less than T1 T2 soup of theta 1 theta 2. And then you get this expression. Difference of bilinear transformations applied to v1 v2. Now, I want to have something here. I'm going to eventually use the continuity of d2f at x naught, right? So it's better if I write things down in this form. So for a bilinear transformation, a bounded bilinear transformation, the norm of B V1 V2 is always less than the norm of B times the product of the two norms of V1 and V2. And that's what I'm applying over here to B, which is this difference, right? The difference between these guys. This is B. So if I do that, I get less than or equal to absolute value T1 and absolute value T2 times product of the norms times the difference between these bilinear transformations. We're almost done. Let's see why. Because now remember that my goal was to prove that phi of T1 T2 divided by T1 T2 converges to D2F of X naught. And so I'm just going to divide over here. These guys cancel, these guys cancel. And what I'm left with is just the sup of the difference between the second derivative of X naught plus something small minus second derivative of X naught. So okay, there's a sup here, but you shouldn't be scared of that. Just saying, I'm taking a sup over theta 1, theta 2. They're getting smaller and smaller as both T1 and T2 approach 0. Therefore, you can even say, well, okay, this point here is some x, and the distance between x and x naught is less than absolute value of theta 1. Under this restriction, is less than the absolute value of T1 V1 plus T2 V2. And of course, this goes to 0 and T1 and T2 go to 0. So this point here approaches this point here when T1 and T2 go to 0. Now remember that our assumption was that the second derivative is continuous at x naught. Therefore, when I move closer and closer to x naught, the second derivative is converging. And this norm here goes to 0. And now we're done. Now we've shown that we've reduced everything, so we wanted to bound this quantity, and in the end was only a continuity estimate for the second derivative, which we know is continuous, so this goes to 0, and everything's fine. Because now I know that this guy here is upper bounded by something that goes to 0, it's also lower bounded by something that goes to 0, so it goes to 0. And that's it. So maybe if you want to play with this thing with the Taylor series that I described to you, that I told you about, the basic idea is that if you have something like this, then f of x naught plus h is equal to f of x naught, well, up to approximation errors. And then d2f x naught applied to h, everything divided by 2. And by using this and looking at the definition of phi before, you can more or less guess that this should be equal to Ts. You just have to use what's above and bilinearity. So if you accept the wiggles, sorry, T1, T2. So if you accept the wiggles as equalities, then you can see from the formula that you get something like this. And of course, that tells you that you should expect that when you divide by T1, T2, that this is very close to D2F, X naught, V1, V2, when T1 and T2 are both small. But you have to prove that, and in order to prove it, we've applied the mean value inequality twice. We've looked at this expression, minus this difference. We bounded it in terms of the partial derivative with respect to the second variable, and then we get something else. And we bound with respect to the partial derivative with respect to the first variable. And once we do that, we reduce everything to this continuity estimate that I told you about. And well, it's a bit of a tricky proof, but it's if you write this Taylor series thing down, you're going to see that it kind of makes sense. We're going to come back to that when we talk about the Taylor series. So yeah, that's it for now. Thanks.